This is the way of represent the biosensor using two capacitors, right? Just an example, you can use another model. This is the one of the models that people use quite a lot for modeling biosensor measurement data using impedance spectroscopy, right? Again, the same curve. So at the end, what you have is like, for example, you have the gold electrodes here. You have the glass, a piece of glass. The gold electrodes are printed inside the glass here, on top of the glass, and we have the analytes here, bounding. It's like covering the gold electrodes, and it's functionalized with a enzyme, and the enzyme is looking for a virus, for example. And once you put blood on it, if the blood sample contains virus, the virus is attracted here, is bounding, so there's a chemical reaction holding the virus here because there was a bonding. And the amount of bonding elements here will cover the electrodes, and the covering area will change the spectra of the signal. And changing the spectra of the signal, then we can say, using the model, if the sample is positive or not, for example. And you can use for virus, bacteria, fungus, any type of bacteria as well. So will depend on what? The chemical analytes here. Will depend what we put here that we want to bound. Oh, we are looking for fungus. Let's put something here that attracts fungus. We want to detect dengue. Dengue is a virus. Oh, let's put something here that contains the RNA of the virus, a piece of it, and put it there, just waiting for the dengue, the virus contained in the blood sample. It can be saliva as well. I'm saying blood because it's the most common, right? As you can see, people have also been using bioimpedance spectroscopy using microfluidic device. Look, it's a very narrow tunnel, and this is the molecule which is being attracted to pass through this tube here. As the molecule pass through here, it can be a virus, bacteria, just a cell, it can be a red cell. Do you know how the people counting cells? They use this. This tunnel here is very narrow, one cell at a time. There's no way to have two cells. There's no space, only one. And the cell just cross here. And crossing here, the field will change. Then, look. And we have a positive, 1. And another cell, 2, 3. And you can count cells using conductivity. Nowadays, the technique counting cells is 1. And also can say how big is the cell. Is it a big cell, a small cell? What type of cell it is? Depending on the spectra as well. The amount of conductivity. Nowadays they don't use spectra, they use conductivity. Okay, they have a table containing the response of the conductivity, which for different types of cells. Okay, and that's the ones work that we have been doing here in UDESC, in our lab. We've been doing this type of setup of electronics, building, printing this with a gold. We have been using this sputtering technique for vaporized gold on the metal here. And then we put frequency, we calculate the impedance spectra, that's the impedance modulus, that's the frequency. So the size of the cells, look, the size 250, 500, 1 millimeter. Depending on the size of the cell, the spectra changes as well, because the interaction with the electric field change. Okay? And another one is we have used an impedance spectrometer from Zurich Instrument, and we have been building printing in biosensors using graphene in a printer, 3D. We built this geometry, is very small, and we are measuring the amount of conductivity of the solution that we put in here. As you can see, bigger image is hydrophobic, and that means the sensor doesn't like water. Hydrophobic, okay? Like this, look, and the drop is there. If you shake a bit, the drop of water will go away easy and look like that the electrode is dry. And as you can see here, for me it's also impossible to see sometimes. It's too small. Dry electrodes. And we put water and we take the water back and we measure again. If it's just to see if the electrode can return to the same data. Here, this is saline solution, green. Okay? And this is saline solution, this is an acid. So depending on the type of the solution we're putting there, the spectra change, therefore the real part, the imaginary part of the impedance change as well. Look, and also the beginning of increasing change instead of here is here, and this is frequency. So there's a shift in frequency that we can calculate as well. So we can extract a lot of information in order to put in a decision tree algorithm, for example. And that's the emerging of the bioimpedance. Also, hydration, disease diagnosis, as I said. That's the future. And the future actually is that we are going, at the end of the day, we are going to wear all type of sensors. For example, electroencephalography, now they're using eyeglass, the smart glasses containing camera, smart mask as well containing biochemical stuff, electrocardiography, electromyography, wristband containing all sort of SpO2, heartbeat. So now, at the end, in the future, we are going to use is as a wearable sensors. Okay, there are some sensors that is not biosensor itself, but in a sense, each type of sensor in connection to the body, to the biological sample, measured in vivo, can also be considered biosensor. Okay, sensor measuring biological samples, biological sample in that case ourselves. And the future of bioimpedance analysis, personalized nutrition and fitness plan. Now people are interested to see if for example, if what they are eating is actually good in terms of, does it convert to free fat mass or not? Nutrition point of view is if just to see not only exercise, but you depending on what you want, eat, to see the amount of free fat mass is increasing or not. Are you losing or gaining free fat mass? It's important for nutrition. And then we may use as a wearable sensor to see it. And the best way of looking at it is using impedance spectroscopy. Early disease detection. You can prevent. Looking in the signal in a real time analysis, you can see if something is going to happen or not. For example, epilepsy. Okay, now they are using a tiny circuit board inside the brain, looking in real time the ECG, electroencephalography signal, to see if one epilepsy signal is coming. Okay. Optimization of medical treatments as well. Now we are, in that case, what we can see here in our case in UDESC, that we are developing a watch, a glucose watch, a device for measuring the glucose level non-invasively. We use a lot of sensors, and 4 of them is bioimpedance sensor. And you can, during a device, you can use all sorts. Nowadays they are using, this is a bulky devices, yeah? Bulky devices for bench, okay, for labs. This is all are not developed for human, not connection with, just ex vivo, okay, in vitro, you can use this device in the lab. But for those one which need to have more safety issues, then you go for wearable devices, portable devices, smartphone-based devices, which is powered by a battery. And then you are safe in terms of human use. But also, if you don't want it, you can design your own system. You just need a current, a signal excitation and a measuring system. And you just need to buy some chips. For example, AG5940, one device which is a phase analyzer straight away, just to power on. Two electrodes, you need a cable, and that's it. Of course, you need to connect to a USB to a computer in order to get the data in and do your processing as well. What I'm saying is that you can do it a lot, even low cost devices. That would be one future in time, that we put a power on a device, and the device straight away just start inject the current to the sample, measure it, and give you the result. That's the future design for BS system. Challenging the limitations. Well, accuracy, reliability issues. So that's the challenging, accuracy. Real time, label-free detection and analysis of metabolites. High sensitivity and specificity, that's important. In order to the doctors, the clinical doctors, trust in your data, you have to have a high sensitivity. Non-destructive analysis, that's the challenge. Minimal sample preparation. For example, if you want to analyze blood, you don't need to take a liter of blood. You just need some drops, a few milliliter, or even more than 1 milliliter of blood in that case. Well, it can be milk as well, but anyway, urine, saliva. Limitations is user error and variability. Interpretation of the user, that means the model is not good, the model is not reliable, because you need a model by the end of the day. If your model is not good, does not represent what's going on in your real world, that means even you have the best in the world hardware, but the model is horrible. And who designed the model? You, the user. So the interpretation of the data is also important. Ethical consideration, you need to be ethical because you are dealing with a biological sample. Sometimes it's in vivo, that means you need to to do that. And that's some regulatory markets. As you can see, the bioimpedance. This is in terms of money is increasing quite a lot since 2018. So it's expected that that's increase in the use of bioimpedance, the amount of money, each one for each part of it. Middle East doesn't change quite a lot. Latin America also, but Asia, Pacific, Europe, North, it's growing quite a lot at the end of the day. So that's the expectation for 2030. Market growing quite a lot. There's a lot of competition in the market using bioimpedance. And we expect that the potential impact on the health industry will be bigger using, because it's a very safe technology. As I said, development of sensitive and selective biosensors for specific analytes. So that's the point. If you want to detect specific microorganisms, you have to build up your specific biosensor for that. Interaction of biosensor with miniaturized portable devices, point of care testing, that's the future. But it's very hard to do that. In terms of electronic, you have a lot of problems. Standardization and validation of biosensor platforms for reliable and reproducible results as well. That's not. But the opportunities in the opposite way, development of biosensor with higher sensitivity, selectivity, and stability, that's opportunity that people, when I'm saying opportunity, that means that's what I put here, that I believe that people should focus on it. Okay? Focus in incorporation of biosensor platforms, artificial intelligence, machine learning, data analysis, and interpretation. We have a lot of data. How to deal with a lot of data, a lot of information, light, pressure, bioimpedance, spectra, force, SpO2, heartbeat, ECG. So a lot of data. So how can you put everything in one box and interpret it and give more accuracy for the diagnosis? Why not using machine learning? So how can you interpret this? Exploration of new application of biosensing platforms in various fields such as biodefense, biomanufacturing, and bioscience. As we are going smaller, some field of research which was not possible 20, 30, 40 years ago, now is possible because the electronic is closer, is getting smaller by day, and also incorporating with biosensors. So, conclusions: bioimpedance-based biosensing platform have the potential to revolutionize various fields because of you can get high specificity, high sensitivity as well. There are several trends in bioimpedance sensors, for example, using lab on chip. As electronic is smaller, people are using sensors together with the chip and doing, as we say, organ on a chip or lab on a chip. Design of bioimpedance-based biosensors involves several keys, yes, and the components work together to detect the quality specified by molecules. This is important for biosensors, and as I said, you can design your one biosensor depending on the specific biomolecular interaction that you want. Virus, what type of virus? Fungus, what type of fungus? Bacteria, what type of bacteria? Are you, right? And can be used in water, air, blood, any fluid. To fabricate biosensors, various chemical functionalization can be applied. And with the new advance of new materials, now you can use that as well. And that's it. Thanks very much for attending this tutorial seminar. And that's my contact, Bertemes IEEE. That's my WhatsApp. You can send me a WhatsApp if you have more questions or the interest, and also want to come to research here in our university. There's a opening places for you to come to do some research on biosensors. Thank you very much.